Dear students, after studying this module, you shall be able to know what is a molecular ion, learn about the fragmentation pattern and the factors which affect it, identify how fragments are generated in mass spectra, and evaluate some important mass spectra of organic compounds. Now, let us begin with the introduction of fragmentation patterns. The ionization of the sample molecule forms an entity known as molecular ion that not only carries a net positive charge but also has an unpaired electron. This molecular ion entity then is actually a radical cation, and it contains which is odd in number. In a case where a molecular ion has a lifetime less than few microseconds, it is not possible to observe it, as the time span of its survival is too short. It is difficult to interpret a mass spectrum without the presence of a molecular ion peak as a reference peak. Although it is fortunate that most organic compounds generally do give a mass spectrum with a molecular ion peak. Now, the organic compounds not giving a molecular ion peak in their mass spectrum respond successfully to the use of milder ionization conditions. Students, let us emphasize on the fact that aromatic rings, other conjugated pi electrons and cycloalkanes are among some of the simple organic compounds which are able to form the most stable molecular ions. Highly stable branched alkanes like alcohols, ethers, and highly branched alkanes usually tend to show the greatest tendency towards fragmentation. Now, the molecular ion undergoes fragmentation in a mass instrument called a mass spectrometer or a mass spectrophotometer. The fragments obtained from the mass instruments upon fragmentation and their nature give us immense information about the molecular structure of the organic compound in question. For most of the compound students and their classes also, the fragmentation pattern is very characteristic. Most compounds and their various classes have a very characteristic and a unique fragmentation pattern. Now, what are the important factors you must be thinking which are responsible for fragmentation of a particular compound? Now, stating them, students. First and the foremost is the energy of the molecular ion and the fragments which are formed from it. Second, of course, is the stability of the bonds in the ions. Third is for rearrangements, that is considering the steric factors, like it is easy to move a hydrogen atom than a whole group. Fourth factor is, students, stability of the formed ions or neutral particles resonance stabilization, such as an acylium ion which is formed. Now, students, I would like to state here Stevenson's rule. This rule is very important while considering fragmentation pattern in case of mass spectrometry. It states that when fragment ions form in the mass spectrometer, they always almost do so by means of unimolecular processes. These processes that are energetically most favorable give rise to the most fragment ions. The important postulate of the Stevens rule is that most probable fragmentation is the one that leaves positive charge on the fragment with the lowest ionization energy. In other words, students, what I mean to say is fragmentation processes that lead to the formation of more stable ions are favored over processes that lead to the formation of less stable ions. Now, after having studied the Stevenson's rule and the factors which affect the fragmentation, now I would like to discuss with you, students, the types of fragmentation involved. The extra energy during the collision with incident electrons places the molecular ion in a highly excited vibrational state. The vibrationally excited molecular ion may be unstable and it may lose some of its extra energy by breaking apart into various fragments. If the lifetime of the molecular ion is greater than 10 raised to power minus 5 seconds, a peak corresponding to the molecular ion will appear in the mass spectrum. However, on the other hand, molecular ions with lifetimes less than 10 raised to power minus 5 seconds break apart into fragments before they are accelerated within the ionization chamber, and these broken up fragments, they enter the mass analyzer. In such cases, students, peaks corresponding to the M/Z ratio for these fragments appear in the mass spectrum. For a given compound, not all of the molecular ions formed by ionization have precisely the same lifetime. Some also have relatively shorter lifetimes than the others. Now, what happens as a result? As a result, in a typical electron impact mass spectrum, one observes peaks corresponding to both the fragments as well as the molecular ions. Often, fragmentation processes involve the loss of a fragment which is electrically neutral. That means it has no charge. The fragment is absent in the mass spectrum, but its presence can be easily deduced by the difference in the masses of the obtained fragment ion in the mass spectrum and the original molecular ion peak. Now, an OE positive radical can fragment in two ways: a cleavage of bond to create an EE plus, that is an even electron cation, and a radical R dot, we are representing the radical with R dot, or cleavage of bonds to create another odd electron radical, which is represented by OE positive dot. That means it has a positive charge and odd electron, it has an extra radical charge also, which is represented by a dot, and a closed shell neutral molecule N. An EE plus, that is an even electron cation, on the other hand, can only fragment in one way cleavage of bonds to create another even electron cation and a closed shell neutral molecule represented by N. This is also called the so-called even electron rule. The most common mode of fragmentation involves the cleavage of one bond. In the process, the odd electron cation radical yields a radical R and an even electron cation fragment ion. Cleavages that lead to the formation of more stable carbocations are always more favored. When the loss of more than one possible radical is possible, a corollary to Stevenson's rule is that the largest alkyl radical, because it is more stable, will be lost preferentially over the others. Now, after having studied all this, let us come to different types of fragmentations. Different types of fragmentation are sigma electron ionization, second one is radical site initiation, third one being charged site initiation, and the fourth one is rearrangement. Now, this rearrangement, which I said the fourth one, is also known as popularly the McLafferty rearrangement, students. Now, sigma electron ionization, the first type of fragmentation category. Let us go into details of this. The fragmentation in molecular ion of alkane takes place as now we have shown you that here you can see that alkanes are getting fragmented into a radical and a cation. Example is that of a homolytic dissociation in 2-butanone, which is a ketone. The acylium ion formed by the loss of largest alkyl radical is most preferred, as I said, according to the Stevenson's rule. Now you can see how this ion gets fragmented into different parts and how it is shown in the mass spectrum. Now you can see the fragmentation of 2-butanone in the mass spectrum. Now you can see molecular mass is 72 and how it fragments into m by z of 43, which is the fragment ion peak, which is the acylium ion, which belongs to acylium ion. Now let us come down to the discussion of radical site initiation, students. In some molecular ions, fragmentation occurs by donation of an electron to form a new bond to an adjacent atom concomitant with cleavage of other bond to that atom takes place in some molecular ions. This radical site initiated fragmentation is one of the most common one bond cleavages and is more commonly called as alpha cleavage. This alpha cleavages may occur at saturated or unsaturated sites that may or may not involve a heteroatom. Take a look at this figure in which it is explaining you the radical site initiation type of fragmentation. In the first one, you can see it is taking place in saturated molecules. The second one includes unsaturated heteroatoms in which radical site initiation is taking place, and you can see an odd electron radical is generated in case of unsaturated heteroatoms. Coming down to allylic molecules. Now here you can see an allylic radical is generated, whereas as you can see above in saturated and unsaturated ones, the normal radical and a radical cation was generated. Now the fourth one, students, is the retro-Diels-Alder or double alpha cleavage. In this you can see a retro-Diels-Alder mechanism is followed using radical site initiation. Another example, students, is the formation of stable allylic carbocation by using this radical site initiation in case of 4-methyl-1-hexene. Now you can see this clearly in the mass spectra of this compound, where you can see that the mass is 99 and how this carbocation, allylic carbocation, is formed, which is more stable. Let us come down to the third category of fragmentations, that is charge site initiation. This charge site initiation or charge site initiated or inductive cleavage, students, is often indicated in a fragmentation mechanism by the symbol I. This involves the attraction of an electron pair by an electronegative heteroatom that ends up as a radical or as a closed shell neutral molecule after fragmentation. When alpha cleavage is a fragmentation of odd electron cation only, inductive cleavage can operate on either odd electron cation or an even electron cation, students. Now you can see here how the charge site initiation is taking place in an odd electron cation and an even electron cation, giving rise to various charges on the respective fragments. Now the fourth one, as I told you, rearrangement, but we popularly call it as McLafferty rearrangement because it was first described by Fred McLafferty in 1956 and is one of the most predictable fragmentation patterns next to the simple alpha cleavages as we have described. In this process, students, a hydrogen atom on a carbon 3 away from the radical cation of an alkene, arene, carbonyl or imine, a so called gamma hydrogen, is transferred to the charge site via a 6-member transition state with concurrent cleavage of a sigma bond between what were original beta and gamma carbons. For simplicity, students, the mechanism of the McLafferty rearrangement is usually drawn as a concerted process. So you can see here this is drawn as a one-step concerted process. So because of it, let us make it more simple. Now cleavages which form the carbocation which is more stable are obviously favored because I have already discussed that according to the Stevenson's rule. Thus, ease of fragmentation to form ions increases in the given order. Now you can see On the left hand side, we can see cations which are more difficult to cleave rather than the right hand side which has the most easiest to cleave cations. In branched radical cations, the largest group is preferentially lost because branching will give you tertiary radical cations which are obviously more stable than the primary ones. Now you can see this order clearly in this order which we have placed from left to right. One or two bond cleavages, they are other types of cleavages, students, apart from the ones we have described, the four types we have described, but this is also important to study. Fragmentation may involve one bond or two bond cleavages. One of the most well known modes of fragmentation involves the cleavage of one bond. This process, students, yields an odd electron neutral fragment and an even electron fragment ion generated from odd electron molecular ion. The neutral fragment that is lost is radical and the ionic fragment is carbocation type. Now let us look at the example of fragmentation via the cleavage of one of the bonds. Now you can see here how cleavage of one bond takes place and how the fragmented ions are formed. The next most important type of fragmentation, students, is the cleavage of two bonds. In this, the odd electron molecular ion yields an odd electron fragment ion and an even electron neutral fragment, usually a small molecule of some type. Let us see here how it is formed. Now you can see how the odd electron molecular ion is yielding a odd electron fragment ion and an even electron neutral fragment in these alkenes which are formed as fragments. Now apart from these, students, there are many other fragmentation patterns that are followed by many compounds. They are rearrangements other than McLafferty, migrations of groups, and secondary fragmentation of fragments which are also possible as fragmentation patterns. And they must also be considered while looking carefully at a mass spectrum obtained for an organic compound. Now let us study the fragmentation pattern in few important compounds. This section of the module discusses briefly the fragmentation pattern in some of the most commonly occurring classes of organic compounds under study these days. First of all, I would like to take up alkanes are characterized by strong molecular ion peaks. The fragmentation pattern contains clusters of peaks which are 14 mass units apart from each other, which represents the loss of CH2N, that is CH2 whole bracket N, CH3 type of skeleton. As the carbon chains become more highly branched, the intensity of the molecular ion peak decreases because the cleavage into fragments also increases. Straight chain alkanes have the fragments that are always primary carbocations. Now since you know that they are unstable, thus fragmentation is not usually favored in straight chain alkanes. As is seen in the mass of hexane, as we have shown you as a clear example, now you can see it has a molecular weight of 86.18, and you can see how in straight chain alkanes with not that much of chain length, how the fragmentation is taking place and how the fragments are lost. Now coming to fact that a functional group having a heteroatom Y containing non-bonding valence electrons like nitrogen, oxygen, sulfur and any halogen, etc., they drastically affect the pattern of fragmentation of a compound. Let us take up the brief discussion of alcohols. The intensity of the molecular ion peak in the mass spectrum of a primary or secondary alcohol is usually rather low, and the molecular ion peak is often entirely absent in the mass spectrum of a tertiary alcohol. Cleavage of the CC bond adjacent to oxygen usually occurs in alcohols. A loss of water may be seen in the spectra of 3-pentanol as an example that we have taken, Now students, it has a molecular weight of 88.15. Now 3-pentanol, let us see how it is showing the fragmentation pattern in the mass spectrum. Now as you know, it will form a secondary carbocation, so fragmentation pattern is definitely going to be there. Now you can see we can have the fragmentation here at 41 with the loss of water and the other fragmented ion peaks also after 59, that is after loss of secondary carbocation which is formed, and then water is lost to give you 41 as an M by Z fragmented peak. The molecular ion peak of an aliphatic aldehyde is usually observable, and we are going to discuss this here in the next example of aldehydes and their fragmentation patterns. Now the molecular ion peak, as I already told you, is usually observable in case of aldehydes, but it is generally weak. Principal modes of fragmentations include alpha cleavage and beta cleavage. If the carbon chain attached to the carbonyl group contains at least 3 carbons, McLafferty rearrangement, as briefed to you earlier also, is also commonly observed. Aromatic aldehydes also exhibit intense molecular ion peaks, and the loss of one hydrogen atom via alpha cleavage is a favorable process. In aldehydes, cleavage of bonds next to the carbonyl group results in the loss of hydrogen, that is molecular ion less than 1, or the loss of CHO, molecular ion less 29. The mass spectra of 3-phenyl-2-propanol, or let us say cinnamaldehyde as another word for it, is taken here as an example. The molecular formula is C9H8O and the molecular weight is 132.16. Now you can see how the fragmentation occurs. First is the molecular ion peak, and then at 132, then you can observe molecular weight -1, that is at 131, as I already stated. Now students, in this figure you can easily observe how cinnamaldehyde and its fragments are generated. You can see clearly, first of all, the molecular ion peak at 132, then -1 at 131, then at 103 with the loss of CHO group, then at respectively 77 and 51 with the respective fragments as we have shown here with red lines. In case of aliphatic amines, let us take another example of amines now. Molecular ion peak may be very weak or totally absent. Alpha cleavage dominates in aliphatic amines. Fragmentation pattern of N-butyl amine, that is C4H11N, with a molecular weight of 73.13 is clearly shown in this figure. Now you can see, as I stated, it has a weak molecular ion peak at 73, which is very small in intensity. However, with the cleavage, you can see here the fragment peak at 30 has a good intensity. Let us come down to the discussion of carboxylic acids and its fragmentation pattern. Aliphatic carboxylic acids generally show weak but observable molecular ion peaks. Aromatic carboxylic acids, on the other hand, show strong molecular ion peaks. In short chain acids, peaks due to the loss of OH, molecular ion less 17, are observed, and COOH, that is molecular ion -45, are prominent due to cleavage of bonds next to the C double bond O, that is carbonyl group. The mass spectra of 2-butanoic acid is shown here or taken here as an example. It has a molecular formula of C4H6O2 and a molecular weight of 86.09. Now let us see what happens. Since you can see here the allylic carbocation is very stable, that is what will be formed, and the COH will be lost. So now you can see, because it has a molecular weight of 86, the small molecular ion peak is observed, and then the fragment ion at 69 and then 45 and 41 it is observed due to the loss of stated fragments, which are shown here with the red lines. Now let us consider briefly the fragmentation in esters. Fragmentation in esters is specially facile, but it is usually possible to observe weak molecular ion peaks in the mass spectrum of methyl esters especially. The esters of higher alcohols form much weaker molecular ion peaks, and esters of alcohols larger than 4 carbon atoms may form molecular ion peaks that fragment too quickly to be observed. In esters, fragments appear due to bond cleavage next to carbonyl group, that is alkoxy group loss, that is loss of OR group, and hydrogen rearrangements as can be seen in the mass spectra. We have taken an example here of ethyl acetate with the molecular formula of C4H8O2 and molecular weight of 88.11. Now you can see here we have a molecular ion peak which is very small, which had to be there, but it is too small to be observed, and then we are having the fragments at 61, 45 and 43. Now you can see the fragmentation pattern obviously by the red lines we have shown here in the molecular formula when it is dividing into fragments. Let us now discuss ketones, students, and their fragmentation patterns in their mass spectra. The mass spectra of ketones show an intense molecular ion peak. In case of ketones, major fragmentation peaks result from cleavage of CC bonds which is adjacent to the carbonyl group. The pattern of fragmentation is similar to that of aldehydes as briefly described. Stevenson's rule is to be kept in mind while considering the cleavage of alkyl groups especially. Generally, students, acylium ion is formed by alpha cleavage in ketones and aldehydes. In case of 4-heptanone, we have taken this as an example here. It has a molecular formula of C7H14O and a molecular weight of 114.19. Fragments appear at M by Z 71 and 43. The cleavage pattern is shown clearly in the figure, and you can see how the patterns are, how the molecular ion cleaves off to fragmentation patterns, and it is showing fragments at 71 and 43 respectively. McLafferty rearrangement is also possible when carbonyl group of ketones is attached to at least one alkyl group, that is 3 or more carbon atoms in length. These examples shall help you students in the better understanding of detailed mass spectral studies of various compounds and other functional groups discussed in further modules. Let us now summarize this module. The ionization of the sample molecule forms a molecular ion that not only carries a positive charge but also has an unpaired electron. The molecular ion then is actually a radical cation, and it contains an odd number of electrons. The molecular ion of a fragment undergoes fragmentation in a mass spectrophotometer. The nature of the fragments gives information about the structure of the molecule. The various types of fragmentation are sigma electron ionization, radical site initiation, charge site initiation, and rearrangements, popularly known as McLafferty rearrangements. Cleavages which lead to the formation of more stable carbocations are generally favored, and generally this is known as Stevenson's rule. In branched radical cations, the largest group is preferentially lost. The molecular ion peaks present in alkanes are of low intensity generally. The pattern of fragmentation shows a cluster of peaks 14 AMU apart, representing a loss of CH2NCH3. A functional group having a heteroatom Y containing non-bonding valence electrons like nitrogen, oxygen, sulfur and various halogens drastically affect the pattern of fragmentation of an organic compound.